Here we're exploring curl of a vector field in space. So let's begin by noting that while the divergence of a vector field is defined by the dot product of the del operator and the vector field, the curl of a vector field is defined by the cross product. So let's begin here by letting our vector field F be defined by components FGH, and we also want to let the del operator be that vector with components ddx, ddy, and ddz. So to compute the curl of our vector field, we want to now take the cross product of the del operator and that vector field. So here we go. We have del cross vector F, our vector field. So again, we have the del operator ddx, ddy, ddz, and we are crossing this with our vector field defined by the components f, g, h. So using the definition for the cross product here, let's put this into a 3x3 matrix. So we have our first row is the unit vectors, I hat, j hat, k hat. Our second row is the del operator. So we have ddx, ddy, ddz. And our third and final row here is the components of the vector field, f, g, h. And remember, we are taking the determinant of this 3x3 matrix to get the formula for our cross product. And so since it's been a while since we've seen the cross product, let's think about the 2x2 minors for each one of these elementary or these unit vectors here. So we're going to have the 2x2 matrix ddy, ddz, gh, and this is multiplied by I hat minus the determinant of that 2x2 matrix, which is defined as ddx, ddz, fh multiplied by j hat plus the determinant of that 2x2 matrix for unit vector k, which is ddx, ddy, fg, and that's all multiplied by unit vector k. And so now taking the determinant, applying that crisscross multiplication here for these 2x2 matrices, we are left with the partial derivative of h with respect to y minus the partial derivative of g with respect to z multiplied by I hat minus the partial derivative of h with respect to x minus the partial derivative of f with respect to z multiplied by j hat plus the partial derivative of g with respect to x minus the partial derivative of f with respect to y multiplied by k hat. And so this is the differential notation for the curl, or for the cross product of del in our vector field. And we can convert this to the equivalent subscript notation and say that this is the partial derivative of h with respect to y minus the partial derivative of g with respect to z, I hat, minus the partial derivative of h with respect to x minus the partial derivative of f with respect to z times j hat, plus the partial derivative of g with respect to x minus the partial derivative of f with respect to y, k hat. So this is how we attain the formula, or the vector here, for the curl in 3 dimensions. So this is the curl of the vector field f. Now alternatively, sometimes we'll see this written as follows. So this is an equivalent form. We can say the partial derivative of h with respect to y minus the partial derivative of g with respect to z times I hat. And now if we take this negative here and we distribute it through to both terms, we can rewrite this as plus the partial derivative of f with respect to z minus the partial derivative of h with respect to x times j hat plus the partial derivative of g with respect to x minus the partial derivative of f with respect to y, k hat. So these are, again, equivalent forms for our curl. So now that we see where the curl of a vector field in space comes from, we're officially ready for our definition. And so we say that the curl of a vector field defined by some vector f with components x, g, h that is differentiable on some region D in 3 dimensions is defined as the curl of vector f, and this is equal to the cross product of the del operator with our vector field. And we just derived the following formula for the curl, and it is the partial derivative of h with respect to y minus the partial derivative of g with respect to z, I hat, minus the partial derivative of h with respect to x minus the partial derivative of f with respect to z, j hat, plus the partial derivative of g with respect to x minus the partial derivative of f with respect to y, k hat. And so this gives us the formula for the curl in space, or in 3 dimensions. And one final love note here before we go ahead and look at examples together is I want you to think about what's going to happen if the curl of the vector field, or the cross product of del and the vector field, is equal to the 0 vector. So if the curl of a vector field is equal to the 0 vector, what is this telling us about the vector field? And so we use our 2-dimensional definition and Green's theorem here to remind us that if the curl is equal to the 0 vector, then the vector field is said to be irrotational.